MAE 242, recitation 10. This recitation will be all about boundary layer theory stuff. Hopefully your professors have gone over that, at least moderately well. If not, I'll just ask questions and I'll explain everything that I need to. But so for this first one, we want to determine the distance x equals x critical, the critical x length, over the flat plate where the boundary layer for kerosene at temperature of 68 degrees Fahrenheit begins to transition from laminar to turbulent flow. So in this case, we've got a flat plate, right? So we've got a flat plate, and so what boundary layers are all about is it's due to the viscous effects of whatever fluid is flowing over that object. Obviously, previously we've taken a lot of stuff to be inviscid, that there is no viscous forces involved, but obviously in the real world, air, kerosene, water, whatever, has some sort of viscosity to it. And that manifests as a boundary layer due to the shear stress, where the velocity of the wall has to be 0, and so you get a boundary layer going there because of the shear stress as you go up along the boundary layer. So this is what's going on here pretty much. So here's our flat plate, here's our velocity coming in. And then, so let's say we're starting right here, we get, as the flow hits this plate, we get a big boundary layer that starts to form, right? And the boundary layer thickness is called delta. This doesn't involve this, but just background, that's what it is. And we also know that right when it starts to hit the plate, everything's all cool, everything's all laminar. But at some location along the plate, let's say, let's call this x critical right here. Once it hits a certain Reynolds number, it transitions to turbulent flow. So again, the streamlines are nice and smooth, and then once it hits this, it transitions to turbulent, and so everything gets all shaky and stuff. So for this, this is what we're trying to find. We're going to find out where that point is. It's all based on Reynolds number, right? So let's get all of our parameters going. So first we have this velocity here is 4 feet per second. And then, it's not given in here, but it's given in my notes. We have kinetic viscosity, mu is 25.4 times 10 to the negative 6. This is square feet per second, right? And so now, what we're going to do, whenever you have any sort of question like this, boundary layer stuff, always try and find a Reynolds number, okay? So in this case, Reynolds number based on just some x location. This REX means Reynolds number at a particular point, right? So REX equals V times whatever x location you're at over kinetic viscosity, right? So let's plug this in. Get REX equals 4 over 25.4 on the other side. Some x value, whatever length you're worried about. Right? So we want to say, well, how do we end up finding where this critical location is at? Well, it comes from the definition of when a boundary layer goes from laminar to turbulent. And that happens for flat plates and airfoils and things like that, external flows. That transition point is about 500,000 for Reynolds number. Anything below that, and it stays laminar. Or, it's always a range because there's a transition zone. So once you get right at 500,000, you start flirting with it a little bit. But don't worry about that. We won't test any edge cases like that. But anyway, everything below 500,000 is laminar. Everything beyond that is turbulent. So really easy. Just set your RE, set your Reynolds number, set equal to 500,000. So we have 500,000 equals 4 over 25.4. And now we're going to call this x critical, because that's what it is. Solve for x critical. Solve for the critical axis. So it's 3.175. So literally that easy. That's what it was. So, given this, we know once the flow has moved 3.175 feet across this plate, it transitions from laminar, nice and smooth, to turbulent. Okay, and that defines a lot of different flow characteristics, so you'll see later. It's very important to know where that transition zone is, especially if you're like a hardcore engineer or doing stuff like that. It's very important to that. You can have all sorts of flow separation characteristics. But any questions there? That's super basic one. Really easy. Not bad. Cool. Okay, let me erase this and we can start getting going on problem 2. Problem 2 is a little trickier, but all 3 of these are pretty short, so don't worry. Moving on. The sense one is going to have like drag coefficient stuff going on. So for this one, we've got a sine, right, exposed to a 20-mile-per-hour wind on a standard day. It's going to drag on the sine if the sine is aligned lengthwise to the wind, so it's like hitting the edge, or if it's crosswise, so it's smacking the face, right? And so take a wild guess which drag is going to be higher. Obviously, the one where it's just straight up smacking the face, right? So for part A, everything is going to be dominated by just the straight up friction drag, right? So for part A, we're going to assume that there's no width, like there's no depth of the sine, right? It's just, it's like a paper sign. Obviously, there's no real like depth to a piece of paper. So first off, for any sort of friction drag stuff, we want to find, it's called the wetted area. And essentially what the wetted area is like the surface area. Think of it like that, right? And we call it S, right? So S is some area. And in this case, the wetted area is what is the area, the surface area that the fluid is touching. Okay? So in this case, it's just 2 times 12 times 6, the 2 sides. So that's all the air is touching. 2 times 12 times 6. This is 144. Right, 144 square feet. Okay, so now the defining equation for friction drag is VF drag friction equals 1/2 rho V squared times S times CVF. Where if you go into some textbooks, you'll see this parameter right here called Q. That's also called the dynamic pressure. You see it written like that. Don't get afraid. Q is 1/2 rho V squared. And S is obviously the wetted area. And the CDF is your friction drag coefficient. And friction drag coefficient is based on the Reynolds number. Okay. So I'll say CDF was a function of Reynolds number. So once again, we can find the Reynolds number. So let's do that. Let's see, let's call our kinetic viscosity. It'll be given to you if you need it. Let's call it 1.621 times 10 to the negative 4. This is square feet per second. Okay, so let's find Reynolds number, right? So RE equals VL over nu, where we're gonna call V, we're gonna convert it to 29.33 feet per second. That's what it is. Yeah, if you do the conversion, it's 29.33 feet per second. And then the length we're talking about is the 12-foot length, right? So times 12 over 1.621. Right. So we end up getting a Reynolds number of like a little over a million of 2.17 million. So obviously very turbulent. That's 4 times higher than 500,000. So turbulent. Go straight up. And so now we can use our turbulent equation for the friction coefficient in the turbulent case. And this looks like this. Okay. It's like CD EF equals 0.455 over parentheses log base 10 of the Reynolds number to the 2.58 power minus 1700 over RB. Alright, and sometimes you'll see just the left-hand side of this being used. The right-hand side of this takes into account the transition effects. Sometimes you'll see a problem that says, oh, assume the boundary layer is totally turbulent. Like, there might be a trip on the surface of the thing that makes it completely turbulent from the jump. In that case, you don't really need that. But in any case, I mean, 1,700 divided by 2 million, that's a pretty small number. So it's not going to make a huge difference either way. But it'll make an appreciable difference. So if you have to add it, add it. But anyway, do all that math, plug everything in. We get CDF equals like 0031 or something. 0031. Right. Okay, cool. Now the only thing we need, we just need the density again. Now I'll check density up here. Density is 0.002379. This is slugs per cubic foot. Yeah, gross. Okay. Anyway, now plug everything in. Not everything. We've got all kind of everything. So we've got EF equals 1/2 times 0.002739, whatever it was, times 29.33 squared times 144 times 0.0031. Right. So we got friction drag. Straight up friction drag is very small, obviously, as you know. 0.456 pounds. Or 2.03 newtons. So obviously very small, which makes sense. Lengthwise, when you're touching it lengthwise, not much is going to be going. I don't remove this. But that number should kind of make sense. Obviously, if you're out, I'm sure all of you have had to carry something really flat like that in the wind, and you're lengthwise to it. Pretty small drag force you're feeling. So now for part B, this is a different sort of concept. This has to do with drag on blunt bodies, is what it's called, because you're hitting something just straight up right in the face. So you'll have like a face drag coefficient, a surface drag coefficient. And we'll just give you these. They'll be in a table. In this case, it'll be like you'll get a table that has different drag coefficients based on the base to height ratio. So in this case, we have base to height ratio of 2, right? Base over height equals 2, right? Because it's 12 or 6, right? And so using some table, you will get a CD equals 1.2. All right, and that's like the total drag coefficient. Okay, we call that the total drag coefficient. So now same exact thing. Total drag. Total drag is the same equation as that. Total drag is still 1/2 rho v squared. Except in this case now we need the frontal area, so AF times CD, or AF is just 12 times 6. 72 square feet. All right. So let's plug in those numbers. You get D equals 88.33 pounds over 392. Or 392 units. Right? Which makes sense, obviously. When it's a blunt object like that, and then straight up on the face, the total drag is going to be a hell of a lot higher than if you're just talking about friction drag, right? Pretty intuitive there. Cool. Any questions there? And these drag equations, they're pretty cut and dry. That's just what they are. It comes from, if you guys remember seeing that like drag coefficient equation, sort of CD, right? Now this comes from Python stuff. Remember how we used to say, we're dealing with like a drag force, non-dimensionalized, and you would always end up getting CD equals F over, rho V squared times something like L squared, right? Well, what's L squared? L squared is an area. Boom. And then we just slap the 1/2 on there because of like math reasons. I'm not going to go into convention stuff. Anyway, that's where that comes from. That's why I did that stuff. Because you didn't know. Because you wanted to know. Cool. Okay. It's definitely a snake. An area is just a square. Yeah, cool. Anything with that? This last one will just be another riff. It's bad boy. Pretty chill out. Cool. And I will also say, like, the professors can only make this concept so hard on an exam because you only have like 2 weeks to really do anything with it. So it's not like it's gonna get all that crazy. You could do I'm telling you, you could do an entire PhD, multiple PhDs on boundary layers. It is such a huge field. It's really interesting. If you feel so inclined, you'll take like good time for this class. We learn all about it. Anyway, continuing. So there's all the key stuff. Yeah. And another thing you should take away from this is like, we make those implicit assumptions a lot because look how less drag there is in the friction case compared to just the total case, right? It's 0.5%. So obviously, if push really comes to shove, we need to simplify your equations. You can call it implicit and be pretty cool. All right, lastly, we got a semi truck shown figure. It has a total drag coefficient based on the frontal area of 0.85. Frontal area of the truck is 9 square meters. So like, in this case, a lot of times they'll just give you the total drag coefficient. You don't really have to like find it yourself. They'll give you a table, they'll just give it to you, whatever. So part A, super easy. So I guess let's call this define all the variables. So it's like V, the velocity is 30 meters per second. It's called density. Let's call it 1.225, it's just air. And then let's go viscosity, whatever. This is a weird number. Just 1.825. This is Pascal something. Alright, so part A, we're also going to our CD. And then frontal area AF is 9 meters. Okay, literally. Plug in all those numbers. We have A, we have total drag equals 1/2 rho V squared AF times CD. Plug everything in. We don't even need to. So we got our total drag straight up. That's 4217 newtons. So quite a bit. Which makes sense. I mean, we had a semi-truck going pretty fast. Of course, I'm quite big at 4.2 kilonewtons. It's not very steep. Okay, part B is of course a little trickier. So part B, we're going to assume that the bulk of the friction drag comes from the sides and the output. We're assuming there's no airflow underneath it. There's not much, so it's fine. We can ignore that. And those are the dimensions, and it's still traveling at 30 meters per second. So part B, again, we need to know that wetted area. We need to know the surface area that is actually being touched by the air. And we're going to assume that like the cab of the truck, we're just dealing with the box part, we're not dealing with the front of it. So we have S. S is obviously, you have 2 sides that it's dealing with. So 2 times 16 times 3. And then plus the top that's going over. So that's 16 times 2.5. not too bad. So now, again, we know we're looking for the friction drag, and that's, you know, rho v squared s times CDF. Where, again, CDF, friction drag coefficient, is a function of the Reynolds number, so let's find the Reynolds number again. So it's equals 1.225 times 30 times the total length, which is 16, that's 16 meters long, over 1.8. This Reynolds number is also very big. It is 32.2 million. And then so once again, like a Reynolds number, all a Reynolds number tells you is the ratio between the momentum forces and the viscous forces in the flow. So obviously, if you have a really fast moving flow or a really long thing, viscous forces are going to be less because it's just such a big thing and flows so fast. You're going to have momentum, right? So I'll plug this into our CDF equation. Because obviously it's turbulent, you know. So CDF again. 0.455 Cool. Plug this in, get everything. CDF equals 2.4541. So now, boom, we have pretty much everything we need. So plug it in, friction drag. Grand total friction drag equaling 183.98 newtons, 184 newtons. So again, much less than the total overall drag, which obviously. If you guys want to know, okay, the reason for a lot of this stuff, generally what dominates in a flow, especially with a big truck object like this, is pressure drag from behind, okay? As you're driving through, you know, let's say we've got the big truck here, and this is another box part of it, right? So, you know, we've got the big box, and we've got all this flow coming up over. All this flow coming up over and over the sides and whatnot. And you know, there's a little bit of friction drag going on from the viscosity of it. But what really happens is as it's driving forward, it's punching a hole in the air right here, right? So as these come down, it creates a big area of low pressure, LP, big area of low pressure back there. And you get all these swirling vortices that come through here. Which is why if you have a big truck coming past you and you're like walking on the sidewalk, if you above me, there's a big area of low pressure behind it. And that area of low pressure is pulling the truck back. It's really sucking it back. So that's a lot of drag. It's called pressure drag. Okay? And that's a big part of, again, like when a plane stalls, there's a big area of low pressure behind the airfoil and pulls it back and it's stalled. A lot of stuff like that. And that's like layer separation and stuff like that. A little more complicated, but for what you need to know, pressure drag is usually what dominates the drag force that dominates flows like this. Cool. Any questions with that? Pretty sweet. All right. Sounds good.